Hello students, welcome to this lecture in which we're going to talk about Green's theorem. So let's recall what we have done in the last lecture. When f is equal to the gradient of f is a conservative vector field. F is a conservative vector field. And also we can notice the fundamental theorem, of the line integrals applies. So we can denote f to be equal to the function p of x and y and the function q of x and y as its vector components. And if p sub y is equal to q sub x and both are continuous, then f is a conservative vector field. So this is a summary from the last lecture. So let's think a little bit about 3D space. So in the 3D case, for function f, which is equal to the gradient of little f, if f is given by three components p, q, and r, we need p sub y equal to q sub x, p sub z equal to r sub x, and q sub z equal to r sub y. And all partials are continuous. Right, just to remind you what things we need to check in 3D space. Alright, so next move to the Green's theorem. Which is main discussion for this lecture. This is just to review how to deal with 3D case. Alright, so to compute certain types of integrals, over certain regions, one can just can just compute an integral over the boundary of the region. Compute an integral over the boundary of the region. And that's the Green's theorem. So let's try to put it down. So our theorem, which has a name of Green assigned to it, and how does it go? It goes the following way. Suppose that C is a piecewise smooth, simple, closed curve. We're also going to suppose that C is the boundary of some region S. In the xy plane. What else do we need to suppose? We need to suppose two functions. So suppose m of x and y and n of x and y are continuously differentiable, and we already discussed what it means. It means not only derivative exists, but the derivative itself is a continuous function. So where is it continuously differentiable? It's continuously differentiable along C and also in S. All right, so that's all we need to consider. Then what would be true in this particular case? In this particular case, we have the following, that double integral over this region S of a partial of n with respect to x minus the partial of m with respect to y dA is equal to, and the new notation here, new notation is this integral is over C, but since C is closed, when C is closed, people put a little circle here to denote that C is a closed curve, so it starts and ends at the same place. So this circle to denote that circle denotes that C is a closed curve. That's all it denotes. F dot dv, sorry. F dot dv, where f is equal to mn, and C is traversed in the positive sense, and positive sense just means counterclockwise. All right, so let's try to prove this Green's theorem. To prove this Green's theorem, unfortunately the proof is not that easy, so we'll do a little bit of hand waving, but let's look at the general idea of this proof. So suppose, so easy case first, suppose that S looks like a rectangle, looks like so let's put it here. Okay, so maybe I'll move to the next page so I'll have more space. Okay, so we have x, and we start at A and we go to B, and this is x equals A and this is x equals B. Then this C1 will be equal to some function g of x. This is C2, which is just a vertical line, and this is our C4, and our C3 will be on top, which is just some f of x, So we can think of C, as the sum of C1 plus C2 plus C3 plus C4, and also C2 and C4 are parallel to the y-axis. Right, and this is some kind of a function here. And some kind of function over here. All right. So let's start building. So we're going to consider the integral over the C, and it's closed, obviously goes back to where it started, of m dx. So we have to split it up into 4 integrals. One is over C1 m dx plus 1 over C2 m dx plus the 1 over C3 m dx plus 1 over C4 m dx. Now we have to notice that if we calculate the integral of m over C2 dx, which would be the same integral as over C4 dx, then we're going to get 0. We're going to get 0 because we don't really move in x direction, right? So we're going to conclude that the integral over c of m dx is equal to the integral from a to b of m of x, but for y we can put g of x dx plus the integral from b to a of mx, and for the top, for y, we can put f of x. So f of x dx. And what we can do over here, if we want to switch the limits of integrations, it's our regular integral, we have to switch the plus into a minus. So we're going to get integral from a to b of m of x g of x dx minus the integral from a to b of m x f of x dx. All right, so everything is good, but the last thing I want to do is to take these two terms, and since the limits are the same, put them into the y expression, but I would like f of x to be before the g of x, so I will factor minus. So minus the integral from a to b m of x f of x minus, again I factor out minus, so this term becomes positive, but this term becomes negative, x g of x dx. Okay, so here we're going to do a little bit of a recall from calculus 1. So fundamental theorem of calculus. Theorem of calculus from calculus 1. It tells you that if you take derivative of the integral from a to x f of t dt, you're going to get f of x. That's the fundamental theorem of calculus. So if you take an integral from a to x and you take derivative of it, you're going to get f of x. Alright, so that means we can keep moving forward using this idea over here. And what do we get? We still have negative a to b, but then we introduce this idea. So we will write the integral from g of x, then f of x over here, d dy of of m of xy dy dx. So we move from this side to this side. All right. So what does it mean over here? This means that it's going to be negative, and you see y goes from g to f, so it's exactly our region S. So we can put S over here, and here we can put the partial of m with respect to y dA. This is our dA. Alright, so, and then for n it's the same way. So in a similar way, the line integral for the closed line C of n dy will be equal to the double integral over S partial of n with respect to x dA. And conclusion is the integral over the closed path C m dx plus n dy is equal to the integral of dn dx minus dm dy over dA. All right, so we assumed our region was really easy. What happens if we have something like this? We could have the region to be like, so what's going on over here? We have a function on the left, we have a function on the right. Let's call this g of y and this f of y, and we have a straight line on the top and straight line on the bottom. So what we can do with this region is easy to deal with. We can just rotate it, right? So we can rotate the region and put it on the side to get the previous one by pi over 2 to get the first case. We can do this. What else could happen? We could have the region to be something like this, like function on the left, function on the right, function on the top, and function on the bottom. Right, so we can have something like k of y, g of y, f of x, and h of x. And regions do not have to be symmetric. So what we can do, we can take each region and subdivide it. We can take each region, subdivide each region into pieces, into subregions. So we can take and do something like, can take this and then have something like this and then something like that. Okay, and then this region over here would be one of our cases that we studied before, and this one we need to subdivide more and get it out. So basically, conclusion is the regions get more and more complicated, they can be broken up, into more and more, into more and more easy pieces. So basically, you just have to have more subdivisions. And it should work. So we used regions that are called convex. So if you draw a line from one point to one point, it's always going to be inside. That's what convex means. So again, if you take 2 points on the border and draw a line between them, it's always going to be inside the convex regions. So can it be done for regions that are not convex or non-convex regions? So let's make a comment about it. So the regions S that we used are all convex. So again, what does it mean? The line between any 2 points, on C is always inside. So what does it mean for us? We had something like this: function, straight line, right? So no matter which line you take between this point and this point, it's always going to be inside. Right? So any line will be always inside. Something like this. So this still can be done. This still can be done with non-convex regions. So what does it mean the region is non-convex? That means some lines will not be inside, well, they will go through the outside part, like if you have something like this. Right, so your line between this point and this point lies outside. So this is non-convex region, but the theorem would still work. So we did a lot of theoretical exercise, theoretical things like theorem. Let's look at the example. So in this example, we're going to suppose that C is the boundary of the triangle whose vertices are 0, 0, 1, 2, and 0, 2. So let's quickly look at what we have for this triangle. So we have 0, 0, we have 0, 0, we have 1, 2, 1 and 2, and 2 and 0. So that means This is the triangle that we have. So this point here is 0, 2. This point over here is 1, 2. And the only line that I don't have is from this point to this point. So let's start calling it C1, C2, and C3. So our C is C1 plus C2 plus C3. We're going into the positive direction. What do we want? We want the integral over this closed line or closed path C of 4x squared y dx plus 2y dy. So what we need to do, we're going to split it up into the 3 parts. We're going to split it up into the 3 parts. So it's going to be the integral over C1 of 4x squared y dy. This is dx, sorry. dx plus 2y dy plus the integral over C2 of 4x squared y dx plus 2y dy plus the third integral over C3 of 4x squared y dx plus 2y dy. So let's start with C1. So C1, we can, in C1 we have y equals to 2x. This is C1. So we calculate the slope. The slope is rise is 2, run is 1. So it's 2 over 1 times x because y-intercept is at 0. So that means y equals to 2x. And we need to parameterize it. So going to parameterize. So let x equals to t when t changes between 0 and 1. So this would imply that y is equal to 2t. So what does it mean for dx? Dx is derivative of t, which is 1 times dt, and dy is equal to 2 times dt. 2 times dt. So what does it mean for us? Over C1, we take the integral when t changes from 0 to 1. Or for x we put t, so it's going to be 4t squared. And for y we put 2t, so we get 2t dt plus 2 times y, which is 2t. And for dy we put 2 dt, 2 times dt. So we're going to get, what do we get? We get 4 times 2, which is 8t cubed. And here we'll have 8t plus 8t dt. And it's evaluated from 0 to 1. So we have 8t to the 4 over 4 plus 8t squared over 2 evaluated from 0 to 1. So 4 and 8 gives us 2, and 8 and 2 gives us 4. If we look into the future, 0 will zero everything out. So we have 2 plus 4 if we plug in 1, which gives us 6. So now we move to C2. So C2 is this line over here, which is y equals 2. Y equals 2. Then dy is equal to 0. And we want x to, so x has to be between this point and this point. So from 0 to 1, right? This is 0. So that means x to go from 0 to 1, from 0 to 1. Actually, I'm wrong. 1 to 0, because we're moving counterclockwise. So let's try to do that. Let x be equal to 1 minus t. Then when t is equal to 0, we're going to get 1. And t is going to be 1, then x was going to be 0. So it's like a mathematical little trick. And we'll let t to change from 0 to 1. In this case, dx is going to be negative dt if we calculate derivative of this function here. So we're ready for our setup. Let's try to do the integral over C2. The integral over C2 will be equal to integral from 0 to 1. So what do we have? We have 4x squared y. So we put 4x squared is 1 minus t squared times y, which is equal to 2. And we have negative dt for dx. But since dy is equal to 0, the rest will just zero out. The rest will be just 0. So we have 4 times 2, which is 8. 1 minus t cubed over 3. And then we have to put a minus here. Minus 1 to compensate for this negative t, so it's going to be negative 1 here, and this negative 1 is over here, which will divide into a plus. Again, why do we need this minus? Because of the chain rule. If we differentiate this function, we would need to multiply by the derivative of 1 minus t, which will be negative 1, and so everything will zero out. Again, if you're not sure, then you do the u substitution, where u is 1 minus t to calculate it. And we want to evaluate it from 0 to 1. From 0 to 1. So what happens if we plug in 1? If we plug in 1, 1 minus 1 will be 0, so this will zero out. But then if we plug in 0, 1 minus 0 will be 1, so we'll have 1 cubed, which is 1. So it's 8 over 3 with a minus because we subtract this part. So negative 8 over 3. Alright, so the last thing left is to calculate the integral over C3. So for C3, let's go back to this picture. We need to use this line where x is equal to 0. So x is equal to 0 for C3. But if x is equal to 0, that implies that dx is also equal to 0. And we want y to go from 2 to 0. Because we're standing over here on the top and we want to go all the way to the bottom. So 2 units down, 2 units down. All right, so the easy trick is to say y equals to 1 minus t for t between 0 and 1, like we did before for x. But this will only give us, it will go from 1 to 0. We want it to go from 2 to 0, so we need to multiply by 2. This way it's going to go from 2 to 0, because 0 times 2 is still 0. All right. And so if we simplify it, we're going to get 2 minus 2t. 2 minus 2t. So basically what it means, if we plug in 0, it's going to be 2. But if we plug in 1, it's going to be 0. Because 2 minus 2. But this implies that the derivative of y, which is the differential of y, will be negative 2 dt. Alright, so we're done with the setup. So we say the integral over c3 dot equals to the integral from 0 to 1 for t. So we have, since dx is 0, this part will 0 out, so we only have this part. So that means it's going to be 2, and for y we put 2 minus 2t, and for dy we put negative 2 dt. So what does it mean for us? That means so that means what? We have negative 4, which is 2 times negative 2, and then we have to find the antiderivative of 2 minus 2t. 2 minus 2t. Right? So we're going to get 2t minus 2t squared over 2 evaluated from 0 to 1. Alright, so cancel this part. Alright, so if we look into the future, 0 will 0 everything out. And if we plug in 1, we're going to get negative 4, 2 times 1 minus 1 squared. So this will be 1 times negative 4, so negative 4. So we have to take this answer for C3, we have to take this answer for C2, and we have to take 6 for C1. 6 for C1. So finally, we say that the integral over C is equal to, for the whole thing, is 6 minus 8 over 3 minus 4 equals to negative 2/3. It's a long procedure, took us like 15 minutes to do. But what if we use Green's theorem? Use Green's theorem instead of this long procedure. So we want to use Green's theorem to calculate this integral over closed C, and it's 4x squared y dx plus 2y dy. So we're going to think of this as m, and we're going to think of this as n. Alright, and then the rule says it's an integral over what? Let's go back and check the integral. So again, Green's theorem. Green's theorem says that n with respect to x minus m with respect to y. N with respect. Okay, so that means we take n with respect to x, and we're going to get 0. So it's going to be 0 minus and this with respect to y is going to be 4x squared dy dx. dy dx. The only thing we need is to put our limits of integration, and let's look for each value y, for each value x, let's see how y has to change. Y has to change from this line over here, and we figure out this line over here is 2x. So y has to change from 2x to 2. So that means for y we put 2x to 2, and our x changes from 0 to 1. So what does it mean for us? That means integral from 0 to 1, we take antiderivative with respect to y, negative 4x squared y dx. But before we put dx, we have to put the limits. So it's going to be from 2x to 2 dx. So we have an integral from 0 to 1, So we plug in 2 first. So it's going to be negative 8x squared. Then we plug in 2x, so it's going to be negative 8x cubed dx. So antiderivative of this function is negative 8x cubed over 3 minus 8x to the 4 over 4. Evaluated from 0 to 1, 4 we can divide, so we're going to get 2. If we look into the future, if we plug in 0, everything zeroes out. So only need to use 1. So let's try to calculate it. We're going to get negative 8/3 plus 2. And 2 is actually can be written as 6 over 3. So negative 2/3. But if we go back, what we have gotten here, we also have gotten negative 2/3 over here. So you see, this is nice and easy, just takes a few seconds. This one took us a while. And the last thing for this lecture, which came out to be a little bit long, but let's finish it off. So this theorem tells us that if S is a region described in Green's theorem, then we can say that the area of S is equal to 1/2 of the integral over the closed curve of x dy minus y dx. Okay. So what would be the proof for this theorem? The proof for this theorem is relatively easy. So we'll say let m equals to negative y over 2 and n equals to x over 2. So if it's true, then the double integral over S of dn dx minus dm dy dA is exactly the integral of the closed curve of negative y over 2 dx plus x over 2 dy, which is equal to 1/2 minus 1/2 dA. If you take the appropriate derivatives, and 1/2 plus 1/2 is 1. So if you take an integral of 1 times dA, you're gonna get A. And that's the idea for this integral in this theorem. So if you want to find the area of the region, you can use Green's theorem, in other words. All right, probably a good place to stop this lecture, and I'll see you in the next one.